Welcome to This Explainer. Today, we are going to decode the fascinating, totally invisible math that keeps our digital world running seamlessly. I mean, if you've ever stopped and wondered how you can instantly send a massive, beautiful photograph across the globe in just a fraction of a second, well, you are in the exact right place. We're diving deep into the incredible efficiency of image compression.
Section 1. The heavy data problem.
We all absolutely love high-resolution digital images, right? They're stunning, they're crisp, and they capture reality beautifully. But that quality comes at a steep cost. These images consume massive amounts of data. And without some sort of intervention, this heavy data constantly threatens to bog down our device storage and completely ruin our transmission speeds. Imagine trying to push a giant boulder through a standard garden hose. That is exactly what sending uncompressed high-res images over a network feels like.
So the crucial question we really have to ask ourselves is, how can we shrink these enormous files without destroying the beautiful, essential details of the picture? Because the ultimate goal of image compression is exactly that. It's shrinking the data size necessary to represent images accurately, ensuring we don't lose the core of what makes the image recognizable and, actually valuable.
Now, compression fundamentally splits into two major families. First, we have lossless compression techniques. These include things like Huffman coding, run-length coding, and LZW coding. Then on the other side of things, we have lossy compression, which relies on techniques like vector coding, fractal coding, and, most importantly for our journey today, transformation coding.
Section 2. What is a wavelet?
To achieve true efficiency in that lossy transformation branch, we turn to our unsung mathematical hero, the wavelet. Think of a wavelet transform as a highly specialized mathematical toolbox. Unlike older methods that basically treat all data exactly the same way, wavelets are mathematical functions that split data into different frequency components. This transform breaks down a signal into basis functions, called wavelets. It's just brilliant and incredibly efficient because it analyzes each frequency component with a resolution that perfectly matches its scale.
And this isn't just a one-size-fits-all kind of deal. Depending on the exact need, we can deploy a really diverse toolkit. We've got the continuous wavelet, the horror wavelet, multi-resolution analysis, the fast wavelet, and the discrete wavelet. Each one serves as a totally unique tool in our data shrinking toolbox.
But why choose wavelets over all the other methods out there? Well, they're highly prized because they offer excellent approximation capabilities. They are just phenomenally efficient at compressing smooth data. But here is the real magic of it all. They allow for straightforward customization of their characteristics. Say an image has specific, localized areas with very sharp visual changes, like the sudden, harsh edge of a building against a perfectly smooth sky. Well, wavelets allow us to adjust the smoothness or dial in greater precision exactly where those sharp changes occur.
Section 3. A century of innovation.
Now, this groundwork didn't just happen overnight. It actually began over a century ago, back in 1909, with Alfred Haar's doctoral thesis, which really marked the inception of wavelet theory. As the decades rolled on, the math rapidly evolved. We went from Paul Levy exploring Brownian motion and scientists pinpointing localized energy contributions in the 1930s, all the way to Dennis Gabor pioneering the short-time Fourier Transform in 1946. All the puzzle pieces were finally starting to come together.
Then, as computing power absolutely exploded, the math rapidly accelerated with it. In 1975, George Zweig introduced the pioneering continuous wavelet transform. Fast forward to 1985, and Meyer crafted orthogonal wavelet bases. The very next year, in 1986, Stephen Mollett laid the essential groundwork for the discrete wavelet transform. This whole golden era culminated with a massive, game-changing breakthrough in 1992, when Albert Cohen and Debachis created compactly supported bioorthogonal wavelets that permanently changed how we process digital media, making modern, highly efficient media compression actually possible.
Section 4. The mechanics of compression.
Okay, let's roll up our sleeves and trace the exact journey a heavy source image takes. Picture this. It enters the source encoder, filters all the way down through a thresholder and a quantizer, and then finally passes through an entropy encoder. What emerges on the other side is a highly efficient, incredibly lightweight, compressed image.
Let's break down what's actually happening under the hood during those steps. First up, we digitize the source image into a numerical signal, which we're going to call S. Once we have that numerical signal, the encoder decomposes it into those specialized wavelet coefficients we've been talking so much about. We'll represent those here with the letter W.
From there, the system applies something called thresholding to modify those coefficients from W into a much more refined state, which we'll call W'. We then quantize W prime into a sequence labeled Q. And finally, we compress Q using entropy coding to create sequence E. That sequence E right there, that is your final, highly compressed image file. Through this really elegant gauntlet of filtering and thresholding, a massive file is shrunk down to just fractions of its original size, totally preserving its visual integrity and making it ready to be sent across the world instantly.
Section 5. Real-world wavelet applications.
All of this rigorous math pays off massively in the real world. Beyond just saving space on your hard drive, wavelets are actively doing some heavy lifting across diverse fields. They refine and smooth digital images, effectively reducing visual noise to give us much clearer data. In the security sector, wavelets are used to authenticate fingerprints with absolutely incredible precision. And even in biological research, they're crucial. They actually help scientists identify cell membranes and differentiate healthy membranes from diseased ones. It's truly mind-blowing stuff.
So from a 1909 doctoral thesis to instantly streaming 4K media and diagnosing cellular diseases today, the Wavelet Transform is quite literally a foundational pillar of our modern era. Knowing how efficiently they compress and shape our visual world, the next time you instantly text a high-resolution photo to a friend, you really have to ask yourself just how much hidden, century-old math is seamlessly operating behind your screens right now.